Thank you to the organisers for giving me this opportunity to speak. And thank you to Sven and Sarah for their great introductions of GALAH and GALAH DR3. In my talk, I'm going to talk to you about results that from work by myself and Sarah and Zhidong Gao and Karen Lind and the whole of GALAH. And I'm going to talk to you about one particular element, and that element is lithium. So why do I want to talk about, why am I talking about lithium when, of course, we've got all these 30 elements? And Sven brought up lithium as well, but why is GALAH going to measure lithium abundances for 500,000 stars? Lithium presents us with that classic models versus observers problem, that models will say one thing and then observations say another thing, and it's a question of who's wrong. So I'm going to talk about two of these issues. One is to do with Big Bang nucleosynthesis. So Big Bang nucleosynthesis very precisely predicts the amount of lithium that the Big Bang produced. But when we go and look at population 2 dwarf stars in the halo of our Milky Way, which we think form from this material that should have the Big Bang nucleosynthesis amount of lithium, we see that all stars are lower in lithium than what we expect. And this is known as the cosmological lithium problem or the primordial lithium problem. The other problem I'm going to talk to you about that GALAH is looking at and trying to understand and solve is a problem about giant stars. And that is that stellar evolution predicts that all giant stars should not have significant lithium abundances at their surface. But when we go and look at them, we find about 1% of giant stars have significant lithium abundances. And this is known as the lithium-rich giant problem. But GALAH is really well placed to understand both of these problems. So first of all, solving the cosmological lithium problem. I should say we haven't actually solved the cosmological lithium problem, but it's a nice title to go with. To sort of show this problem graphically, what I'm plotting here is that this is results from GALAH, and I'm plotting dwarf stars that we've observed. And I'm plotting the metallicity of stars against their lithium abundance. And both of these are on log 10 scales. So differences of 1 are 10 times more or less on this scale. And you can see that most of the stars we have in GALAH are in this range between metallicities of -0.5 to plus 0.5. And so that they've got a big range of lithium. But there's a scattering of stars at really low metallicities, -1 through -2.5. And if we had even more metal poor stars, the trend would continue. That you can see all these stars are at about the same lithium abundance. And this has been observed not just by GALAH, but lots of places have seen this problem that all these stars at all metallicities have about the same lithium abundance. And it is significantly lower than the pink line, which is what Big Bang nucleosynthesis predicts. This very precisely, people predict a certain lithium abundance was formed in the Big Bang. And this difference is a problem because we think these metal poor stars will have formed from material that should have had, nothing really should have happened in these stars, and then this material that reduces their lithium abundance down to this level. So this has been known as the cosmological lithium problem, and it's been a problem since the early 80s, and people, there are some ways that you can maybe understand why the lithium has gone down, but no, it doesn't really bridge the gap. So what Zhidong Gao and Karen Lind have been doing is to look at stars on either side of the feature that Sven talked about very briefly, which was the lithium dip. So if you look at stars on either side of this, you see some very interesting behavior, which is the stars that are slightly warmer than the lithium dip, which are the blue stars on this plot. They have a high lithium abundance. And the cool stars on the other side of that dip have a lower lithium abundance. And when you look at the trend of lithium with respect to metallicity, or the lithium with respect to metallicity, that's what the black dot stars are. So the lower one, the lower star line black thing is for the cool stars, and the higher one is for the warm stars. You see that there's a very systematic difference between, consistently systematic difference between these two populations of stars. and that the cool star one runs very nicely on into what you can now think of as a cool star plateau. These are all cool stars. And the warm star one runs very nicely on into the Big Bang nucleosynthesis amount. And you can think of, so this is like a missing warm star plateau. And there is a scattering of warm stars at that abundance. And so what we conclude in this, or what Judong concludes in this paper that's actually now accepted, it got accepted yesterday or the day before by monthly notice letters, is that the warmer stars seem to be preserving the primordial lithium that was produced in the early universe. And so the problem we've always had is that these cool stars, something is happening to these cool stars that's reduced the lithium. And so this has been, the observers have been wrong kind of in the models versus observers problem. It's actually the observers have been wrong to some extent in this case. So, and to answer very quickly the question about why there are so few metal pool warm stars that's just appeared, the warmer stars are going to be more massive, and so they won't have survived as long as what we think is happening. These stars don't actually exist anymore. The other modeling thing that GALAH, models versus observers thing that GALAH is looking at is what is the origin of these giant stars with large lithium abundances. So what I'm plotting here is the surface gravity of stars against their lithium abundance. And you can see that the dwarf stars have a certain range of lithiums. And when the stars evolve off the dwarf, evolve onto the giant branch, their lithium abundance drops dramatically because of their convective zone rapidly deepens, and this causes the lithium to be burnt. This is well understood and well expected. Except we find about 1% of our stars have a really high lithium abundance, and this is really confusing. And so the problem with these stars is nothing else about them that tells you they're lithium-rich giants. They're very consistent, they have no other bulk property about them. And so what Sarah and I have been looking at is to try and understand this in the context of GALAH. And so we've found about 1,300 of these lithium-rich giants. And one of the really interesting things we've found is we can divide these stars in between what are known as core helium-burning giant stars and hydrogen shell-burning stars. So that's what we find is that these lithium-rich giants are about 3 times more likely to be core helium-burning stars than to be red giant branch stars. And the other thing we find is that there is a really obvious difference in the metallicity trends between them. So these red clump stars, there is a clear trend with metallicity of how likely they are to be lithium rich, versus for the RGB stars, the hydrogen shell burning stars, their metallicity is quite, the proportion is quite flat with metallicity, except that they're most metal rich stars. And we found interesting things with rotation rates and with infrared excess. There's all sorts of things that we're being able to pull together that have been talked about individually in the literature, but haven't been sort of pulled together before. And so we're able to really say now that there has to be multiple production pathways that you need. And that we haven't really come up with a model, unfortunately, but it's clear that it could be planet engulfment and it could be binary interactions and it could be all sorts of things, but it isn't one thing that's doing this. Okay. So to conclude, since I forgot to start a timer and I'm not sure how many seconds I have left, GALAH has been able to look at lithium and look at models versus observations and a bunch of different things. We've been able to try and, we're getting somewhere about solving the cosmological lithium problem, and we think it's relating to these warm stars are retaining the primordial lithium abundance. And we're trying to solve the lithium-rich giant problem, and we're really understanding now the marked differences between the lithium-rich giant stars between them when you look at their metallicities and their evolutionary stages and their stellar rotation and all sorts of things that we haven't been able to do before without large data sets like the GALAH survey. Thank you.